you can look for those two procedures. One for recrystallization using a conical vial, so it's slightly different than what you'll be using, but the technique is still ultimately the same. And then one for melting point. The recrystallization has no sound. Sorry, I haven't put that in yet. And then the melting point does have sound and describes a lot about the general technique. Okay, so that one's probably a lot more helpful. Okay. As I'm recording, as soon as I'm done with the recording, I'll go through and listen to a couple of them and decide which one I think is best. And I'll post that as well to that channel. Okay? Just so you're aware, I'm teaching a couple other classes, which means all of those are getting recorded and posted, and I don't know how to sort it yet. Okay? So just make sure you're looking for the right video before you start this. So what we've got on the left-hand image is a recrystallization kind of in process, and the right hand is a melting point. Okay? So we're going to talk about these two techniques, what's going on with them, how to apply them, how to do them, sort of. Okay? Mainly more about the theory. So if we take a look at, again, physical properties and intermolecular forces. So I finally convinced everybody that we needed a slide on this, so they decided to put one in. Okay? So it's a little bit different than what you've seen before, or what I've shown you before, so maybe it'll be more helpful. So you get the different types of forces, the same ones that I talked about before, your van der Waals, which is London dispersion, your dipole-dipole, hydrogen bonding, and your ion or electrostatic forces. You need to be familiar with their relative strength. So ion-ion is very strong. Van der Waals or London dispersion are very weak. Okay? It gives you a general rule on how you can find these things or how to predict these intermolecular forces, and then also provides some examples. So it's kind of nice for that. Okay? How can we go through, let's not even look at applying yet. Let's go ahead and take a look at these molecules. And we want to rank them in order of increasing intermolecular force. Okay? As I've been teaching you this, we'll go through how I would tell you to start. So if you take a look in that lower left hand, it says bond and force. So let's take a look at compound A. What bonds does compound A have? Anybody that's saying hydrogen bonding is not talking about a bond. Okay, you've got covalent bonds. Do you have anything else? We have polar covalent. Which of those two do we want to focus on? Polar covalent. Why should we focus on polar covalent? Generates partial charges, which is giving us some source of reactivity. So we'll initially look at our polar covalent bonds. Okay? So we could then write underneath that polar covalent, right? What does a polar covalent bond give you as far as a force? Dipole-dipole, but now what we can do is move up to the next stage. If we have a dipole-dipole force, we want to see if we can hydrogen bond. Okay? What do we need to be able to hydrogen bond? You need a hydrogen and it's not quite that, but you're very close. The hydrogen has to be bound to a very electronegative element, and there's only 3 electronegative elements that count: oxygen, nitrogen, or fluorine. Okay? We'll never see fluorine. You can ask me after class if you don't understand why. So if you see a hydrogen bound to oxygen, nitrogen, or oxygen or nitrogen, that molecule has hydrogen bonding as a force, not a bond. Okay, so we could then write hydrogen bonding underneath it. We'd go through and do the exact same thing for B, C, and D. And then we'd go through and rank those according to those forces. Okay? Anybody notice an issue with that process? Say if we look at D. It has polar covalent bonds and hydrogen bonding. So if we tried to rank these, according just strictly to the intermolecular force, A and D have the same intermolecular force. It doesn't say equal, it says increasing. How can you tell the difference between A and D? What should we do now? Okay, before we even get to size, there's an easier one. Look for a difference between those two structures. If I look at structure D, what do I have right there?
Double bond.
I have a carbon-oxygen double bond that I don't have in A. That is an extra polar bond, or a polar covalent bond, which is going to generate what extra force? Dipole-dipole. Now it's not just hydrogen bonding versus hydrogen bonding, it's hydrogen bonding versus hydrogen bonding and dipole-dipole. Which one would have the stronger intermolecular force? D. So that would be our strongest, right? That kind of looks like strongest. Make sense? Okay, so now that we know how to look at individual molecules, okay, and rank them based on their intermolecular forces, we'll go through and try to apply this. Okay, and in my opinion, this is an easier application than TLC or column chromatography. Okay, we'll look at the melting point. What's happening at the melting point? What are you doing? Okay, we heard a couple answers there. I'm going to, of course, highlight the wrong answer. Breaking bonds. Are we breaking bonds in this case? No, we're going to break the intermolecular forces that are holding those individual molecules together. Okay? So if we look at the intermolecular force, if we have, say, an ionic force versus a London dispersion force, which one would have the higher melting point? Which one requires more energy to break that force? The ionic one. It's a stronger interaction because we're neutralizing those charges. Okay? So what melting point is going to do for you is allow you to then rank a compound based on ultimately its strength of intermolecular forces. So if we have a very high melting point, we can now start to predict something about its intermolecular forces. What would its intermolecular forces be if it's very high?
Strong.
Very strong forces. What does that mean about the types of bonds? Very polar bonds as well. Okay? So we can start to conclude some things about this. If you take a look at the right, we've got two pictures. Okay? That top one is very, very close to the melting point. How might you tell that that's close to the melting point? So it's still a solid, so it definitely hasn't melted yet. What else? If you look really, really closely at that image, you kind of see some weird pseudo-reflections. That's the molecule sweating. Okay? So it's starting to transition into a liquid, but it hasn't officially started yet. Okay? So when we're looking for a melting point, we're looking for that phase, and now we're really, really, really close. The first drop of liquid we see in that capillary is now the beginning of our melting point. When would the end of the melting point be? When it's all a liquid. Okay? And that's what that bottom figure is trying to show. Okay? So you'll be looking at these capillaries. These are extremely blown up. Okay? They're very, very small capillaries, much like your TLC spotters. Okay? That you're going to be dealing with in lab next week. Okay? So we could go through and start to apply this to intermolecular forces. We just discussed some things or some information about our forces. If we have very weak forces, like van der Waals or London dispersion forces, those molecules are not held to each other very tightly, which means how much energy do we have to put in to break them? Very low amount of energy, which means what happens to the melting point? Very low melting point. Okay? So that's all this chart is trying to show, is to give you a relationship between strong intermolecular forces and a higher melting point. So this question should look really, really familiar, right? Because it's pretty much the same question, except now I say increasing melting point. Which compound would we expect to have the highest melting point? D. Why D? Because it's the strongest intermolecular force. Okay? So we can rank these things accordingly. One note, because this is part of your group activity as far as ranking goes. Noticed a lot of people going through and putting 1, 2, 3, 4. That's good, because that ranks things nicely. What does 1 mean? Okay? Could mean lowest, could also mean highest. So when you write down 1, we have no idea what you're talking about. So if you're going to rank them and number them according 1 through 4, okay, tell me what 1 equals. If 1 is low, write 1 equals low, and we can figure it out from there. Okay, if you want to make sure absolutely, with 4, then write high. Okay, so it's very clear what you're referring to. So let's jump out of melting point, okay, and we'll look at some of the uses. We can use it to identify a compound. So one of the nice things about a melting point is you're transitioning from a solid to a liquid. Okay, what changes as you go from a solid to a liquid? The intermolecular forces are starting to get broken up, true. Do we have a volume change? Not really. Very, very subtle typically. Okay, so there's not much of a volume change as we do that transition. Okay, why is that important? Well, let's say we looked at a boiling point. We tried to boil water here. What temperature would it boil at?
100 degrees.
100 degrees. Let's go up to Denver, Colorado. What's it boil at now? Boils lower. Okay, interesting. The boiling point changes. Okay, what's the difference between going from a solid to a liquid as opposed to a liquid to a gas? When you boil a gas, what's the volume change going from the liquid to gas? It's a huge volume change. Okay? Is volume related to something else that's changing as we move from here to Denver? Pressure. Okay? So because we get a large volume change, we also see a large pressure dependence. When we look at a melting point, however, do we see a volume change? No. So do we expect to see much of a pressure change or a pressure dependence? Also no. Okay? Why is that nice? Well, if I take that compound and melt it here, and then I go to Denver and melt that exact same compound, what's my melting point going to be? The same. Okay? So we can look up and identify compounds based on their melting points. Okay? Which is really nice. We can just compare it to a literature value. Okay? The other thing we can do is use it to establish purity. And that's what we're going to talk about here, and that's why we're doing the recrystallization. Okay, how many of you are comfortable with complex organic structures? Okay. How many of you are comfortable with, say, a box? There we go, okay. So let's, instead of dealing with complex organic structures, let's deal with boxes. So for an example, let's take our pure compound box. And I now want to take a look at that phase transition on going from a solid to a liquid. Okay, well, first off, I need a whole bunch of boxes. So there we go. We now have a whole bunch of those blue boxes all near each other. Okay, what's holding those boxes next to each other? The intermolecular forces along each of those lines, right? Okay, so if there's strong intermolecular forces, what do we expect to happen to the melting point? Should be very high. If they're weak interactions, very low, right? Okay, well, let's see what else we can pull out of this. This box, upper left-hand corner, how much energy does it take to remove that box? Kind of a hard question, so let's change it up. How much energy does it require to remove that box? Give me a number between 0 and 100. 50. How about to remove that lower right-hand box? 50. Why is it the exact same? The exact same intermolecular forces. So if I'm now going to take this solid and slowly increase the heat or increase the temperature, what happens when I hit 50? Everything breaks apart and I now have a liquid. Okay? That's for an ideal perfect single crystal. Okay? How many or how often do we deal with ideal, perfect anything in the lab? Never. Okay? So just by sheer existence, we're not real or not ideal anymore. So we've shifted into something that's a little bit more real, which means those intermolecular forces aren't all exactly the same, but they're pretty darn close. So as we start to increase the temperature, maybe about 49 degrees or 49 units, it starts to melt. And at 50, it's completely done. What we would report is that range. Okay? And if it's a pure solid, we would expect that range to be very, very, very narrow, because for the most part, you're just looking at minor imperfections in the crystal. Okay? So that can tell us something about its purity. The other thing that we could look at is how close that value is to the literature value. If it's close to the literature value, what does that likely mean about the compound? Not necessarily pure. We can kind of draw conclusions there. Say I take an unknown and melt it. It melts at 0 degrees Celsius. What's that compound? Probably water. Why do you say water? Because it melts at 0 degrees Celsius. You're comparing it to that literature. So when it's close to the literature value, okay, you can identify in that case. So if it's a pure compound, we would expect it to be very close to what we expect that compound to be. Make sense? So what happens if we mess with it and we throw in an impurity? Okay, so now instead of dealing with boxes, let's deal with boxes and complex organic molecules. Haha, no, we won't do that yet. Let's add trapezoids. Okay? So we now have an image of an impure solid. What's happened to the intermolecular forces now? Are they the same? No, they've been disrupted. So if we take a look at those same two molecules, our upper left-hand corner molecule and our lower right-hand corner molecule, what would we expect for the energy to remove those? Should it be the same? No. Now it's drastically different. Okay? Which means when we look at our melting point, okay, or our melting range, we get a much broader range in our melting point. Typically would say that's greater than a 5-degree spread. So when we see that first drop to when the entire sample melts. Okay? What else could we potentially predict out of this? Okay, it's nicely covered up. As a guess, it probably has something to do with a literature value, right? Okay, what do you think is covered up? What do you think would happen to those intermolecular forces? Should they get stronger? So look at the picture. Does it look like the intermolecular forces got stronger? No, why not? You see gaps. You see air particles or air spaces. Okay? When we add an impurity, it destroys the crystal lattice, okay? And it weakens all of those forces. So what happens to our melting point value? It goes lower. Okay? Everybody likes to say lower. I don't quite agree with that. Let's go back to that solid. What's low temperature? 0 degrees is typically low, right? If I give you that solid, again, melts at 0 degrees Celsius. That's a low temperature. Does that mean that water is impure? No. Why not? Because it melted at the literature value. It's a comparison. It's not just lower. It's lower than the literature value. Okay? So those would be your two big signifiers for something when you're looking for impurity. So if we now try and apply this knowledge, we can do a mixed melting point. So you're given an unknown compound. Okay? You run the melting point and you get a melting point of 121 to 122 degrees Celsius. What can you tell me about that compound? It's probably pure. Why is it pure? You get a very narrow range. Good. Okay? Can you tell me what compound that is? Okay. If we take a look at these two compounds listed up here, urea and cinnamic acid, both of them have the same melting point. Okay. Can your compound possibly be both of those? No. Okay. So your melting point, because it's based on intermolecular forces, you can change the amount of intermolecular forces enough, even if they're really weak intermolecular forces, to get it to give you a same melting point. Okay. So we have to come up with some other way to identify it. So what we're going to start off with is assume that it's urea. Our unknown is urea. So we're going to take a sample of urea and we're going to mix our unknown with it. Well, if we're right, we took urea and we took some more urea and we put them together and we made urea. So what happens to the melting point? Doesn't change. It's the exact same compound, exact same mixture. What happens if instead we now look at our cinnamic acid? Okay, we take cinnamic acid and our unknown, which we're saying is urea, and we mix them. What have we now done? We've made an impure mixture. What happens to our melting point? It's going to be lower than our literature value and a larger range. Okay? So we can take advantage of that information to help us identify a compound. Okay? We talked about solubility last week, so I'm not going to spend too much time on this. It pretty much comes down to like dissolves like. That's our primary rule. Okay, so if we take a look at a structure like butane, okay, what intermolecular force does butane give you? Whoever said LDF, I like that. That's a shorter thing to write. LDF, London dispersion force. Okay, we now take a look at carbon tetrachloride. What intermolecular force does that give you? What do you think? What type of bonds are in carbon tetrachloride? Polar covalent, which would mean that bond is giving off what force? Dipole-dipole. So the bond is a dipole-dipole force, but what about the molecule? Still London dispersion forces. Why? The geometry of that structure neutralizes those polar bonds. Okay? So if we take a look at butane and carbon tetrachloride, they have the same type of force. Like forces interact with like forces. What would we expect to happen? Soluble. What happens if we now try and dissolve butane in water? What intermolecular force does water give you? We get hydrogen bonding. LDF versus hydrogen bonding, are they similar? No. What does that mean? Insoluble. Okay? So having a control of those intermolecular forces allows us to predict these things. Okay? So we could go through a learning check. It says arrange the following compounds according to increasing solubilities, okay, in water. Based on what I've been telling you, what's the first place or first thing that you should do? How about we write down our forces? Not just the forces of our compounds, but we also need to see how they would interact with water. So we would have to look at the forces, our forces for water, which is hydrogen bonding, and we'd want to compare that to our intermolecular forces for each of the others. Okay? One little thing we'll add on to that. What intermolecular force does this compound generate for you? Ionic. How do you know it's ionic? You see ions. Okay, nice and obvious. It works out well sometimes. What kind of compounds are ionic? We come up with another name for them as a class. Salts. What do you know about salts? They dissolve in water. Okay? So if you see an ionic compound, 9 times out of 10, it's probably more than that, probably 99% of the time, it is water soluble. Okay? The hydrogen, or the ability of water to hydrogen bond, you generate a whole bunch of hydrogen bonding interactions with those ions, making the ions very, very, very soluble. Okay? So if you see an ionic bond, almost always it's water soluble. Okay. So now what we're going to do is apply solubility to recrystallization. Okay? Recrystallization is used to purify solid compounds. So what we're going to do is take advantage of solubility to remove impurities from our compounds. Okay? You've got a procedural summary there. That's something that I've added on. Remember, when I post this, you'll have access to it. Okay? This is in general what every recrystallization procedure is going to do. Okay? This is what you should do when you get into class. It does everything. Okay? So just be aware of that, and we'll look over it later. Did it not move? Come on now. Yep, thought it skipped ahead. So let's take a look at possible things that this could look like. Okay? So we take a look at that first line. What we're going to do is take our solid, we're going to dissolve it. Okay? So our very first step in our recrystallization is to add a whole bunch of impurities. And the goal of those impurities is to break all of the intermolecular forces within our solid compound so that we can then control how they come back together. Okay? So we dissolve everything, we cool it, and in the process of cooling, what we hope is for our solid to reform. Except we don't want it to reform as a solid, we want it to reform as a crystal, or a more pure solid. Okay? Well, we started as a solid and we end as a crystal. Okay? Or we can even say we start as a crystal and end as a crystal. What kind of technique might we call this? How about recrystallization? You get rid of your crystals and you make them again. So recrystallization. So that first image or series of pictures up top, would any of you attempt to do that procedure? Does it make sense to do that procedure? What was the goal of recrystallization? Purify. Would you recrystallize a pure solid? Okay, no, it doesn't make any sense to. Okay? So how would you know if it was a pure solid or not? We could run a melting point. So when we run the melting point, what would we expect to see? Okay, a broad range and a lower value than we would expect for our literature compound. Okay, so we run that test and we decide, yeah, sure enough, we have an impure compound. Okay, so what we're going to do is add a solvent to it, so add some impurity. That impurity is going to go in and break all of the intermolecular forces that are holding all of those compounds together. Why do we need to break all those intermolecular forces? We have to be able to get our impurities out of the solid. How are the impurities held in the solid? Intermolecular forces. So we break those forces apart, and then what we're going to do is cool it. Why would cooling cause crystals to form out of a solution? Okay. If we look again at our solution right here in the middle, we've broken all of our intermolecular forces. What phase does that seem most like? Interesting interpretation of phase. Very true. Not what I was going for. Solid, liquid, or gas. Make it a little bit easier. Okay. A liquid still has some intermolecular forces shifting around in it. Okay. Ultimately, what we're mimicking in that middle is a gas. We've completely removed all intermolecular forces holding our compounds together. Okay. What would happen if we take that gas state and we cool it? What does the gas become when I cool it? A liquid. What happens when I cool that liquid? Becomes a solid. Okay? So one of our observables when we're dealing with solubility is it tends to translate or correlate very closely with phase transitions as well. So when we cool our solution, we hope to see our crystals slowly precipitate out. And sorry, not precipitate out, recrystallize out, okay, which is what that middle part is referring to. Recrystallization is a very slow, selective process. We're individually putting each of those molecules together to form a single crystal. If we precipitate, it's happening so fast that as they form the crystal, they trap, say, solvent molecules in it. But what's the solvent? It's an impurity. So if we do a very fast crystallization, what we're really doing is a precipitation. We're trapping impurities. We just have to restart the whole recrystallization process. Okay? So now we need to figure out an ideal solvent for this. This is a very popular curve that shows up on pretty much every single exam, handout, post-lab assignment I've ever seen. Okay? So it's really, really important to be able to interpret this. Okay? As you should do with any curve or any kind of graph, we should go through and simplify it as best we can before we attempt to interpret it. So what can you tell me about that point? That little red dot. I think I heard someone going with it. Soluble. It's highly soluble, right? We're way high on that y-axis, and we're saying solubility increases as we go up. So we have something with high solubility. Okay? Guess where I'm going to go now? Let's go down to here. What does that point represent? Low solubility, also known as insoluble. How about this point? Low temperature. Low temperature is way too long of a word for me to write, or series of words. Let's try something else. Cold. Okay. How about over here? Warm. Oh, come on. Hot. Let's go to extremes. Okay. So we now have some interpreting or some information already interpreted for us on this graph. Now we have to try and slide stuff into this. I attempted to color code and did a very bad job color coding. Okay. Curve A is the red curve. Okay. That represents what? Oh, it wasn't that funny. Give me a break. Okay. Curve A. So that's our red curve down at the bottom. What can you tell me about that line? It's insoluble. What happens when I heat it up? It stays relatively insoluble. So curve A represents our ideal insoluble impurity. Okay, we want to call it ideal because we want it to stay insoluble. So I could add, say, or try and separate sand from salt. What could I do to separate those two? I could add water. What happens when I add the water? Salt dissolves, sand doesn't. How could I separate the sand now from that solution? Filter. So what I'm relying on is a difference in those solubility curves. If we move to curve B, what can you tell me about curve B now? That's the green top one. Okay, it starts really high solubility and it stays soluble the whole time. Okay. Now we've got curve C, which is the trickiest one. That's our target compound. Okay. If everything worked out well, we could probably purify things by staying in curve A and B. Okay. But we're never going to get perfect situations. So what we need is some solubility relationship where we can make our compound change its solubility. Okay? So it'll start with a very low solubility, and once we add a whole bunch of heat, it'll become really, really soluble. Okay? So that's our ideal situation. If I wanted to separate compound C, or curve C, we'll say it's compound C now, away from compound B, what circumstance would allow me to separate those two? Okay, where are they different from each other? At low temperatures. So if I cool that mixture down, what happens? C is a nice solid and B stays dissolved. Now I can filter. What if I wanted to separate C from A? Now the difference is at high temperatures. So I'd want to keep everything hot when I went through to filter and separate them. Okay, that's the trickier one to deal with. Okay. As far as what you guys are doing in the lab, you're going to end up with two types of impurities, okay, or two types of experiments. So in part one, you're going to purify naphthalene away from a soluble impurity using methanol as your solvent. The glassware that you're going to use is a Craig tube. I tried to find a real picture but couldn't. The Craig tube is that little thing down there at the bottom. It's the glass test tube looking thing that has a wider flange in the middle of it. Okay? That's where you're going to do your recrystallization, where you're going to dissolve all your crystals. So if you watch the YouTube video where I use a conical vial, swap it out for a Craig tube. Follow it exactly the same and you'll be good. Okay? The other part of this is the Teflon inner plug, which is the white thing that sits inside of that. You'll also be using that to kind of cap it. The rest of this apparatus setup is what you'll have to do to remove or to filter your liquids away from your solids. Your TA will go over that when you're doing it in lab. For the second part, it's a lot easier because we'll do the recrystallization in a beaker instead of in that fancy microscale glassware system. Okay? And in that case, you're going to purify benzophenone from an insoluble impurity, okay, using petroleum ether as your solvent. Okay? What you should be able to do is go back to each of these and decide when you should be filtering it. Should it be hot? Should it be cold? Okay, based on what we just talked about. Our last learning check before you're free to run off and do the rest of this handout. Okay, based on our understanding, we want to pick the best solvent to recrystallize biphenyl. So what's our ideal situation? A, B, or C? C. So we want our compound to be both soluble and insoluble. Okay, so let's go through and do this based on intermolecular forces. What intermolecular forces does biphenyl have? London dispersion forces. What does toluene have? Okay, those two forces, similar or dissimilar? Sorry. LDF, London dispersion. Similar. What would you expect about their solubilities? Very soluble, which would mean which curve? B. Is that the right one? No. What do we get for water? What intermolecular force? Hydrogen bonding. Hydrogen bonding versus LDF. Are those similar? No. What would we expect for solubility? Not very soluble at all. Which curve would that represent? Probably A. What does that leave you with? Process of elimination is a beautiful thing. There's your answer. If we take a look at ethanol, we've got two parts of it. One half is our LDF. The other half is our hydrogen bonding. What does the hydrogen bonding side do to our solubility? Increase or decrease solubility? Decreases it. So the hydrogen bonding prevents biphenyl from dissolving. Okay. What does the LDF side do? helps it dissolve. Okay? So what we're doing is by changing the temperature, we're favoring one half of that molecule over the other. So when we're picking an ideal recrystallization solvent, it kind of needs to have a mix of both. Okay? So you now have the rest of that group activity. In theory, you should have all answered everything on the front page now because we just talked about all those answers. As far as that last page, okay, or the back side of it, there's some random little bits of information that might be helpful. So we've got structures for the compounds mentioned that aren't given, and also some boiling points. And then just in case you didn't know, room temperature is right about 22 degrees Celsius. Okay. Before you leave today, make sure you turn in the assignment and also hopefully pick up last week's group activity. If you've got questions, just raise your hand and Saswata or I will be